Induction hardening. It is a method of surface hardening of steels by using high-frequency electromagnetic field. The component is placed in the inductor. When an alternating current is passed through the inductor, it sets up a magnetic field. The alternating magnetic lines tread through the surface of the component, inducing an alternating current of same frequency but in reverse direction. The reverse alternating current passes along the surface of the conductor and is known as skin effect. When the desired temperature is reached, after a set time of 1 to 6 seconds for about 1,000 to 10,000 cycles per second, the surface is quenched by pressurized spray of water. Nitriding. It is the process of surface hardening by addition of nitrogen to the steel surface. Nitride promoting elements are aluminum, chromium, vanadium, or molybdenum. In nitriding process, the steel component is placed in a gas-tight container through which ammonia gas, NH3, is circulated. Container and the component temperatures are raised approximately up to 500 degrees Celsius, from 40 to 100 hours depending on the depth of hardness required. At this temperature, ammonia dissociates and nitrogen is liberated. The liberated nitrogen is absorbed in the surface layer of the steel. Nitrides are then formed close to the material's surface, promoting surface hardness. The case depth is about 0.025 to 0.05 millimeters. Surface hardness is around 1,000 to 1,100 Vickers. Hardening. The steel with 0.3 to 0.7% carbon is heated above 750 degrees Celsius to 900 degrees Celsius, depending on the carbon content, and then rapidly cooled by quenching produces hardened steel. The degree of hardness depends on the carbon content of steel, quenching media, and the quenching temperature. The quenching media can be caustic soda, brine, water, or oil, depending on the rate of cooling required. Hardening material in this way produces internal stresses and makes the material brittle. Tempering. Tempering is a process whereby the hardened steel can be partially softened in order to offset the brittleness. It leaves the metal hard and tough enough to do its job. Tempering consists of heating the material to some temperature below 720 degrees Celsius and holding this temperature for duration of time. This depends upon the mass and the degree of toughness required, and then quenching or cooling in air is carried out. The combination of hardening and tempering is greatly employed with steels and alloy steels to obtain the desirable properties. Straight carbon steels with carbon content below 0.2% are usually not subjected to hardening and tempering processes. Annealing. The objectives of annealing are grain refinement, inducing ductility, stress relief, or a combination of these. Castings, forgings, sheets, wires, and welded materials can be subjected to annealing process. In this process, the material is heated to a predetermined temperature depending on the percentage of carbon content, allowed to soak at this temperature, and then cooled in the furnace at a controlled slow rate. Normalizing. The objectives of normalizing are grain refinement to produce uniform structure, increase ductility, and to improve strength. The casting is heated to about 750 degrees Celsius to 900 degrees Celsius. It is held at that temperature for short time and then cooled in still air at room temperature. The more rapid cooling of the material gives better, closer-grained surface finish. Normalizing differs from full annealing. The difference is that the rate of cooling in normalizing is more rapid, and there is no extended soaking period. Case hardening. This treatment is also called pack carburizing. The steel component to be case hardened is packed in a box made of fire clay, cast iron, or a heat-resisting nickel-iron alloy. Carbon-rich material such as charred leather, charcoal, crushed bone, and horn, or other material containing carbon is used as the packing medium, which is made to cover the component. The box is then placed in a furnace, and the temperature is raised above 900 degrees Celsius. The surface of the component will absorb carbon, forming an extremely hard case. Depth of the case depends upon two main factors, such as the length of time and the carbonaceous material employed. Actual case depth with this process may vary between 0.8 mm to 3 mm and requires between 2 to 12 hours to achieve, depending upon these limits.